that is a specialty type of thing that people, electrical engineers have to know it, and maybe a few other people, but this is not that applicable to anything any of you people should encounter in your career. Transformers are. The next thing is, in the next following chapter, in chapter 9, they have information about diodes. Now, I'm going to cover diodes, and I'm going to cover transistors, both field effect transistors, FET, and bipolar junction transistors. But I'll do it after I cover the topic I'm about to, and it's called operational amplifiers. How many have heard of that term, op amps or operational amplifiers? 1, 2, 3, 4. You'll use them in your laboratory work all the time. MEs will use them, aerospace engineers, probably IEs, but I can't say for sure. So I'm going to start there. This is chapter 10, and I need you to be attentive to me. I'm going to show you the secret, because if you try to read the theory in the book, you're probably going to get a little frustrated, but I'm going to try to make this as clear and simple as possible. So you're going to have to pay attention, because this does not make sense in terms of a linear circuit element, but it works mathematically, and it represents, let me say, the last, well, I'll put it up here, then I'll tell you what I'm talking about. This is the symbol for an operational amplifier. It's a triangle. There'll be two leads. These are the input. One is negative, the other is positive. Typically, they show the voltage with respect to a ground is V negative, and this is V positive. Now, the truth is, the input voltage will be on this side, and somehow will link to that point, but just watch me for now. This is the output. And here, there are only two laws that govern everything about this. I might add, this is called an ideal operational amplifier. Now there are non-ideal amplifiers, but to the first order approximation, for almost everything I know of that you're going to be dealing with and I deal with, you assume ideal. There's no reason not to, is what I'm getting at. Unless you're talking about super high fidelity sound, and if you're going to make an amplifier, I had one kid make a speaker in this very class years ago. He was in 3810, non-double E. He wanted to do a crossover, and he wanted to make a subwoofer for his thing, if you know what that is. Anyway, and he did. That was one of the most, that kid was amazing. Anyway, that's long ago. But if you ever do want to make a high fidelity amplifier, anybody in here, I don't think that's a big driving force these days. High fidelity sound used to be. Well, talk to me before you do anything. I don't care what you say. Now here are the laws, and there's only two. There is no voltage difference between these two. It's going to seem stupid. Well, if there's no voltage difference, how can anything happen? Don't worry about it. You got that? No voltage difference between these two terminals. You could say V plus minus V minus is equal to 0. That will not make sense. And the second thing, this is the only two laws you have to know. Just write them down. The second thing is there are no current. No current can flow into the op amp. All right, in those terminals. You all with me? So there's no current going in and no voltage across it. So the natural question is, why do we talk about it? Because inside this triangle, there are thousands, perhaps, well, hundreds at least, perhaps thousands, even tens of thousands of transistors. This represents one small fraction of something called a very large-scale integrated circuit. You with me? When you buy a package with an op amp, usually you don't buy just the op amp. You buy a whole bunch of operational amplifiers and other chips, all embedded on one small little thing, probably about that big, maybe the size of a silver pearl, $0.50. So how does this, I mean, it accomplishes it by things you're going to learn about that are called transistor circuits. The input is a differential amplifier. These are things I'm just throwing out there as pieces of information, so you know there are a whole lot more to that than a triangle. And there'll also be power supplies. I better put this on here. You'll see a plus VCC and you'll see a minus VCC typically. Sometimes you just see ground. Those are voltage supplies that are DC. Those are of no concern to us. We just care about that triangle, the inputs and the output. Got me? So with that in mind, let me do a problem that you would see. And I'll show you how it does amplification, it does a whole lot of stuff. You ready? So now I'm going to start with a source voltage. For now, I'll just call it Vs. And this can be a time. I'm going to have something with sinusoidal voltage right there. Next, I'll have my amplifier. That's an operational amplifier. Then what I'm going to do is from here, I'm going to come and draw this, and I'll call that R1, and I'll connect it down here, and then I'll connect it to R2 here, and this will go to my V out. Now, here's something that I didn't mention. Where V out is, it's connected right there. You can have current flowing in and out of V out. And the amount of that current will be determined by the input conditions. And I have to show you this. I can't really explain this unless I show it to you. Now, there's one other thing you have to do. Remember I said that the thing that governs the behavior of this, one of the things, is there's no voltage difference, right? You can't leave one of these terminals dangling. Just can't. So the logical thing to do is take this and just ground it. That means it's at 0 volts. I want to be as clear as I can about this. You all follow me? Okay? I'm going to ground this too. I could run lines all over the place. And the voltage output is going to be taken with respect to ground. So this will be V out right here. Just V out. Are you with me? Now, here's how this thing works. And by the way, this is called an inverting amplifier design, and you'll see why in a second. Remember, the thing you always go for in here is you look at the voltage across these two terminals. If you know the voltage at one terminal, you know it at the other. You follow me? There can't be a voltage difference. So if you find the voltage here is 0 volts, can you all see that back there? That has to be 0 volts. The way that's forced to 0 volts has to do with feedback mechanisms buried inside that triangle that you can't get to and you don't need to worry about. But electronically, it'll force that condition to happen. So it's 0 volts here. Now, if it's 0 volts here, I think you can see that this current here, I1, now just let me talk to you about it. You all agree that's 0 volts, right? Can you all see that? That means this current has to be Vs minus 0, or just Vs divided by R1. So let me make it a little clear. That means this I1 here is equal to Vs over R1. And it's that simple. Do you agree with that, everyone? I want to make sure you can see this and understand. It's this simple. And people make this ridiculously hard because they're not in class or they're not listening to me. And then they come to the quiz and it's like, I didn't understand what the book said. You probably won't if you read the book, because it's written at a higher level and it doesn't break it down to the bare bones. This is, yes, sir.
We aren't including R2 in that calculation because...
This is 0 volts here. Do you see that?
Yes.
It has to be 0 volts there, right?
Right.
If it's 0 volts on this side and Vs on this side, we know the current, don't we?
Yeah. Okay.
So R2 would have no bearing on that current. Do you agree?
Yes.
Does everybody see this? Now R2 has a bearing on the output voltage. So the next question is, how much of this current goes into that negative terminal? None. You all hear me? How is that possible? The electronics inside that triangle do that. You don't have to worry about how it's possible. They take care of it. You with me, class? This is an ideal operational amplifier. So where does all the current go? Does everybody see that? That's the only place it can go. If you eliminate where it can't go, you know where it can go. Now, if that current flows there, hear me now, this is where mistakes are made. What is the voltage across this, and I'll call it V2 going to be? Well, as I labeled it plus to minus, it would be I1 times R2. Do you agree with that? Can you see it in the far back? Everybody? I mean, how you can see from the last row, I'll never know, but I applaud you. I wish my eyes were like this. So this is going to be equal to I2 R2. Now listen, I1. I1 times R2. But what is I1? Vs over R1. So this is going to be really Vs times R2, keep watching, over R1. I've got to make sure you see the logic. This is how you analyze these circuits. You can get all sorts of resistor topologies. This is the method you use. Always find the voltage across the input terminals, or the voltage at one terminal, then you know the voltage at the other. After that, you know no current flows in. You determine the currents flowing from the source voltage. That determines the currents flowing to the output. You all follow me? All right, now if that's the case, and this is the actual sign convention, what is V out? Here's where mistakes are made. Listen. Just listen. The way you get V out, you start, and this is the way I do it, at the negative terminal of the volt where you want the voltage, right? Come over here, there's no volts difference between these two. So I come here, this would be a voltage decrease of Vs times R2, R1, right? That means, and I'll get to the point, that means V out here would be minus Vs times R2 over R1. Does this make sense to everybody? Now you'll notice that minus sign implies the voltage output would be inverted. If this was a positive 1 volt here, you would have a minus 1 volt times the ratio of R2 to R1. If it's a sinusoidal voltage on the input, the output would be sinusoidal, but would be 180 degrees out of phase. In other words, if the input's going up, the output's going down. You all follow me on that? So finally, they talk about something, and this is the thing that you'll see mentioned over and over again, and they'll ask for the voltage gain. Write this down. The symbol is AV. A is amplification. The sub V means voltage. Voltage amplification. And it's always a ratio of V out over V in. Well, V out is here, V in is Vs, right? This is really, you're going to see this right here called V in. It's really the input voltage. Here I call it Vs as a source. So if you look at that, it's really going to be minus R2 over R1. And that's how you do that problem. Now I'm going to caution you, don't just memorize circuit topology, voltage gain. Go through the process, because you notice how that's a negative sign there, right? If I would do something, and I would put the input, and I'm not going to do it right now, but if suppose I coupled the input to this terminal, y'all follow me? Then the output wouldn't be inverted. But I don't want to do too much to complicate matters. I want to show you the simplistic way to do the analysis. Are you with me, class? We're going to do a couple of these. Now, it's very simple. One more time. There is no voltage across the terminals here. Whatever's voltage is on the plus is on the negative, period. The second thing is, there is no current into these terminals. That determines the operation of this. Are you, everybody with me on this? Yes? Did you have a question back there? No. Does everybody follow me? I'm going to do some problems. This is actually something that I will hear. This is the simplest stuff you've covered so far. and I've heard it's the hardest. They're extremes. Usually people that say it's the hardest stuff is they didn't show up, or they didn't listen to the lecture. They didn't get the information from me. They try to get it online or reading the book or something, and they're totally confused. Because I've taught this stuff to electrical engineers and non-electrical engineers. And I know if I don't break it down this simple, people get very frustrated and confused. Because the mathematics get a little tedious when you get into the actual mathematics of the electronic circuits that do this. It gets very hard, and this is a first order approximation. So that's an operational amplifier circuit, and the best way to see some of the uses for that, first, you all follow me. If you just wanted to amplify a signal, you didn't care about the phase, suppose it's an audio signal. So an audio signal is 20 to 20,000 hertz. Supposedly you can hear up to 20,000 hertz. Has anybody else heard about this? I mean, do you know the audio range for most people? I mean, it's good to know these things. You know what optical frequencies or wavelengths of the light are. You know what audible ranges. These are things that are useful in all sorts of product designs. So 20,000 hertz is extremely low frequency. You don't have to worry about a lot of design that you'll read about at some point for high frequency amplification. If you wanted to amplify a mic, you know what a microphone is, right? A microphone is a transducer that takes pressure waves and changes them into electrical voltage. That's all it is. It can be done a lot of ways. It can be a piezoelectric chip in there, or it can be an actual diaphragm on a speaker cone. It'll vibrate, and there's a magnetic coupling of voltage induced. It can be done tons of different ways. Doesn't matter. That small little voltage has to be increased. And the simplest way to do it is with an operational amplifier. They're dirt cheap. And you can buy them, and you can make an operational amplifier. There is one condition though. You do have to have voltage sources. They're DC voltage sources. So either you're going to have a permanent battery, or you're going to have to do rectification of wall voltage and turn that AC into the DC voltage you need. So I'm just giving you things to consider down the road if you're doing anything with op amps. By the way, don't MEs have to use op amps to build things? Anybody here in ME that has done that? It was in a laboratory, or what did you have to do it for? How many here have had this measurements lab in ME? You're the only one? Well, I know this because I've talked to mechanical engineers, and they say that they have to know how to do this. So, did you get this theory, by the way, in your lab?
They talked a little bit about it.
Well, you can't build a design if you don't understand that. They probably just gave you the gain formulas. All right, but this is it. Now I'm going to do some problems. We're going to work through this. But one of the other circuits that this is used for are called adders. Now, you know, and you can make it do exactly this. If you would like to, suppose 1 volt was used to represent the number 1, 2 volts, the number 2, 3 volts, the number 3. And you wanted to have some way of quickly adding up all these numbers. We're going to do an adder. You ready? This can be made. This is how. See, this is called. By the way, this is not digital. It's not a digital system. This is an old, ancient, antiquated, analog computer method of adding. And then we'll talk about differentiation and integration. You can do them all with this little device, the operational amplifier. You can do it very cost effectively. It's not hard to do it. So, now let's talk about an adder. Remember that was an inverting amplifier, what I showed you. Remember that? How the output was the negative of the input in terms of its sense. So, this is called an adder. And I'll make the simplest one. So I'm going to call this VA, and I'm going to call it a resistor. Now, sometimes they label these different, but I'm going to call all these R1. Here's VB, R1. Here's VC, R1. tie them all together. And then, we're gonna have all these come in contact with an operational amplifier. That'll be the negative, this will be the positive. We're gonna take the positive lead and ground it, 0 volts. Then, I'm gonna put a resistor here. Now, I'm gonna make this different, but I'll explain why. And this, right here is gonna be my V out with respect to ground. Now this is something you have to get used to. You'll notice I showed you just VA. I didn't write a voltage source for you. You're used to seeing this. You know what I'm talking about, everybody? That's what you're used to seeing. To save space, they assume you understand VA is a measurement of the input voltage with respect to ground. How it got there makes no difference to you. Y'all follow me? It exists. All right? Now, we go through the analysis just like we did before. Listen to me. That's 0 volts. What's the voltage here, class? 0 volts because there is no voltage difference between the input terminals. Does everybody follow me? We got that. So this is 0 volts. Now, if there's 0 volts there, what is the current here? I can call this IA, for lack of a better. What would it be? Just look. No wrong answers. Yes, sir. Does everybody see that? It is literally that obvious. Follow me, everyone? Voltage on this side is VA with respect to ground. This side is ground, or 0, so it's VA over R1. So IA flowing here, VA over R1. You want to take a guess what this is? Can you read my right? VB over R1. You all follow me? Can you all see it, by the way? Over on this side too? Am I shadowing you right here? Can you all see it? All right, so this is VB over R1. And finally, this one is simply VC over R1. It doesn't have to be, R1 doesn't have to be used. They can change, but if I'm doing something that's going to be used as a true adder, they'd have to be the same. Now, what happens to all these currents? Remember, I say this over and over again. How much current goes into that negative terminal? None. How? The circuits inside that triangle make it happen. So all that current has to go this way. Agreed? That's IA, IB, and IC. And they would sum together. Okay? Which makes this voltage right here, that I call V2, equal to simply R2 times IA plus IB plus IC. Does everybody agree with the ideas so far? Based on what I've told you are the laws. No voltage across, no current into those terminals. Now, if that's the case, I'm sorry?
Where is it?
Couldn't hear. Who's,
No.
I mean, if you're asking, don't be afraid. I didn't know.
So you have to divide by R1?
What?
You have to divide by R1?
Well, IA, IB, and IC are VA by
Oh.
R1. I didn't replace that yet. I'm going to, but I just want to make sure everybody sees the logic in this. And you got it? Can you all see that? Like that. Which means that this, and you're ahead of me, is really going to be R2 over R1 times VA plus VB plus VC. Y'all follow me? I pulled the R1 out in front. It's R2 over R1. Y'all see that? Can everybody follow me on this? Far back, especially. And the only thing I've done, VA over R1 is IA, VB over R1 is IB, and VC over R1 is IC. I added them all together and pulled out that R1. Now, if I look at that, what does that make this voltage? And take note of how it's measured. It's measured positive here to ground, right? And if you come around, start at the 0 volts right here, come to here, still 0 volts, right? And then you get a voltage decrease of that. Do you agree with that? Or the output voltage is going to be, I'll just put it down here. V out is going to be negative or equal to negative R2 over R1 times VA plus VB plus VC. And I'm going to show you something. So it would be, if we had R1 and R2 equal to each other, it would be additive of all the input voltages. Do you agree with that? But it has a negative sense to it, right? So what we do is something called an inverter. And there's a lot of ways to make an inverter. I'm going to show you the simplest. An inverter looks like this. I'll put it over here. This is called an inverter. And I'm going to just show you the simplest possible inverter. I'm not saying they're this way in the real world, but it makes sense to do it this way. All right, can you all see this? The only thing this is going to do is, if the signal coming in is VA, the signal going out of this is minus VA. It simply inverts the sign. How does it do it? Well, again, anytime you do these things, I suggest you do them from scratch. That's 0 volts, that's 0 volts, right? Everybody with me? The current here must be Vn over R1. Do you agree with that? That would be, I'll call it In. And that current, I didn't put R1 here, but it should be R1. That current goes up here because none of it can go into the negative terminal. Are you with me? And all that current generates a voltage here. The voltage difference, and I'll just call it V2 for lack of a better term. V2 would be equal to that current, Vn over R1 times R1, or it's simply equal to Vn. The R1s will cancel. You all follow me on this, class? Now that's the voltage from here to here. So the output voltage, start at the negative terminal, come here, 0, 0. It would be a minus, or V out is minus Vn. That's why it's called an inverter. So if I add that stage after this one, and I'm showing you, there's ways to do this, clever ways to do it much more efficiently, but this is the easiest to understand for an inverter. Do you agree with this so far? Very simple. Now you take that and you put it right here. If you want to get a true adder, and forget that, take that and simply have R1 into an operational amplifier, ground that, R1, and now your output right there this V out will actually be this with a positive sign. So it will be R2 over R1 times VA plus VB plus VC. And I have a comment. Are you with me on this? If R2 is equal to R1, it's simply the addition of VA plus VB plus VC. Does everybody see that? That is an old, ancient, analog method of adding voltages. Doesn't require them to be digitized. How many have had anything dealing with digital, any Carnot mapping, gates, JK flip-flops? Have you had digital mathematics, base 2 math, ones or zeros? Have you had it? ME should have, I think. You had what class?
It was like intro to MATLAB.
Yes, MATLAB should have had it. You should have had it in some of the courses. This digital stuff is always base 2. It's either a 1 or a 0. It's either on or it ain't. So like, if you think about the number 2 is 1 0, right? The number 3 is 1 1. The number 4 is 1 0 0. Do you all follow me on this, guys? It's base 2 math. You're used to base 10. I'm just leveling with you. That's what it is. And when you see this, if you're doing digital operations, it would not be a digital adder. All right, that's a different story. So if you're going to get to some point in your careers where you're going to have to do stuff with digital mathematics, and that's all base 2 math that I'll talk about later. Has anybody had encryption courses here? I figure the IEs might, because the stuff, the nature of your business requires it for so much. But how many IEs are in here? Industrial engineers? I know I've got them. I see. All right. Well, if you don't want, maybe they're not here. Maybe they're seminars. Anyway, people are going to do digital stuff. It's base 2. This is not a digital adder. I'm just underscoring that fact because I can hear somebody saying this is not this. Oh, this is an analog adder, but it will work. If these voltages are representing true numbers, if 1 volt here represents the number 1 and 0.1 volts represents the number 1/2 and so forth, then this will be a simple adder, as simple as possible. Okay? Now typically, if you're doing an analog adder, where you're adding 3 signals, typically these are microvolt or millivolt signals. So the output, in order to be something that can be read easily on an oscilloscope, will have an amplification factor of R2 over R1, just to make it bigger. That's it. I'm just letting it. All right? Okay, that's an adder. Anybody want to take a guess how you would do a subtractor? I mean, there's so many ways. What would be one way? I think everybody can come up with one way. Suppose I want to make a certificate that has as an output VA minus VB. Just think about this. Well, the minus VB, let me see, doesn't that sound like an inverter, right? So have VB coming in through an inverter, then coming into an adder with what was VA and VB. Do you all follow me? You can make almost anything. You can have an adder, subtractor, a multiplier, R2 over R1, a divider by something, just 1 over R2. You can do anything you want simply with simple math with that circuit. Well, we're going to get the differentiator and integrator in a second, but before we do, I want to do one more problem, at least one more. I want to show you some of the things that may irritate you, but may not irritate you. And I'm trying to do this in, as far as I'm concerned, in the simplest possible way without driving it nuts with some of the things that can happen. So this is problem 10-10. If you have your books or you want to take note of that, problem 10-10. The reason I'm doing this is some of these at first glance scare people. They say, oh no, you've never done that. In truth, you have the theory to do any of these problems very easily if you just take a look at it. So for this problem 10-10, they're all basically the same idea. Just use the laws I gave you. They have an operational amplifier here. then they have a source voltage here. And then they have a resistor here. I'm sorry, not here. A resistor off the negative terminal. And that resistor is 2K. And they have a resistor tied to here, and that's 3K ohms. And they want to know V out right here with respect to ground. Now, I'm doing this for a reason. It's not quite the same as before. Here we tied an input voltage right to a terminal, right? How would you go about solving this? Take a moment and ask yourself. I want to see how you think about it. I'm not going to call anybody to answer me if you don't want to. Believe me, I'm not that guy. I don't do that here. How many, I'm not going to ask you to do it. How many think they know? I would say more than that. You're cautious. All right, the cardinal thing to remember are the two laws. No voltage across the input. You all hear me? If the voltage here at the plus terminal is Vs, the voltage at the negative terminal is Vs. Don't worry about how it happens. It's internal to the op amp. The electronics make that happen. They force that condition. So if that's the case, do we know the current here? Class? Yes, right. What would that current be? You got Vs on this side, 0 on this. This current would be Vs divided by 2K. Do you agree with that, class? Can you see it? Or not? I'm trying to make sure that I'm not missing something. How many see this? I'm trying to make it as simple as I can. You see it? Or some people are too tired to see it. You were up late, apparently. I don't know why. Tumor's corner looked white. Somebody was out there doing it. It wasn't me. Anyway. Okay, everybody with me on this? Now, if that current's coming here, where did it come from? Can any come from the negative terminal, class? I know I'm repeating myself, but I'm trying to underscore the obvious. No. Where does it come from? From out here. So all that current comes here, right? And that current is Vs over 2K, which makes this voltage, now be attentive here, this voltage, call it V3K, is equal to that current. I'm trying to make it simple, which is Vs over 2K times 3K. Do you agree with that? How many do? Just make sure. Can you all see it back there? All right, so it's really going to be just Vs times 3/2. This plus to minus voltage is 3/2, I'm getting rid of the K, times Vs. Now please just follow me. I mean, that's the voltage from here to here. I'm trying to be clear about that. That's this voltage right here. Can you all see that? All right, what's the output voltage then? Just look and listen, but be attentive. Try to force yourself to be attentive. These are where mistakes are made. You got this voltage, right? But you start at the negative terminal, always, right? Come around here, I get a voltage increase of Vs, right? Vs is here too, right? Then from here to here, I get a voltage increase of 3/2 Vs. Does everybody see that? Making my total output Vs plus 3/2 Vs, or 5/2, or yeah, I'll do it that way, 5/2 Vs. Does that make sense to everybody, the rational approach to it? All right? Now, what's the voltage gain of the circuit? It's the output over the input, which is Vs, right? Can everybody see that's 5/2? what would you do to this if you all of a sudden wanted to design, or I asked you for the resistance value that would give me a voltage gain I'm going to use this one right here. Suppose I don't give you that value. Let me do the whole, I'm just going to erase everything. And this is kind of a typical question that would be asked. Suppose I say I want the voltage gain to be 100. Everybody understand that, right? So, and I'm asking for the value of this resistance that would achieve that. I'll leave the 2K alone. I don't know what that is. I can call it I'll call it R2 for lack of a better term. Y'all with me, class? How do you, yes sir?
In this case, which voltage would be considered your input voltage?
It's the one given, VS.
And is it still defined, the AV, is it still V out
Over VS. The input voltage is VI, V source. Typically you'll see VI because I implies input. I'm not overtime yet. I still got some time. Do you agree, class? All right, so AV is a ratio of what? You made a good point, though. AV is a ratio of V out over, you can call it V in. How's that? Everybody say it? So it's 100, right? Or V out is 100 V in. You agree with this? Now, work backwards. How do I get that resistance? Well, do I know the current through that? Yes, it's right here, right? This current never changed, did it? The current is not a fact. R2 does not in any way affect this current if that's set. You follow me? So I know this current. This voltage here is simply going to be that current, which is Vs divided by 2K times R2. So it's R2 over 2K, right? Y'all see this? Can you read my writing? All right. Now what's the output voltage going to be? Well, we got it here, right? But what is it from the approach of this side? Well, it would be what? What I'm doing is starting. And this is V out here, right? So if I start here, I know I'm going to get VI, agreed? Everybody with me on that? Plus that voltage. So V out is going to be VI plus that voltage, and unfortunately I use VS again. I'll go back to VI plus VI times R2 over 2K. But I know this has to be equal, I mean this is equal to VI times 1 plus R2 over 2K. And that has to be 100 VI, right? I'm just showing you the obvious. Everybody agree with me? Far back? So how do we find out what R2 is? How about we get rid of VI right here? And get rid of that. Everybody with me? So that means 1 plus that is 100, means R2 over 2K is 99. Y'all follow me? And solve for R2, which should be 2 times 99. Does everybody agree with this? All right, now, that is the method that you would use to solve that problem. I'm gonna do one more thing here. I'm looking at these. All right. Okay, I'm going to do one more. This is 621. Now, I'll cover differentiators and integrators next class, but for the quiz, I'm going to ask you to know operational amplifiers. I'm not gonna ask you a transformer problem on this particular quiz. You're gonna get that, but it's not gonna be on this quiz. You with me? After I do diodes, you'll understand why in a bit. So, let me go ahead. Do one more. This is problem 1021. It's a good problem. But I can see how people might have problems with it. Can you all see the circuit, class? You good with it? Can you see it? All right. I'm asking you, remember that those ground symbols are 0 volts. You all with me? So I'm asking you, if you were asked to solve this problem for the output voltage, assume these are DC sources, how do you do it? Where would your starting point be? Would anybody want to make a suggestion? Yeah.
On the voltage difference between the positive.
Well, what is the voltage difference between these two? You're close. It's 0, isn't it? Yeah. There is no voltage difference. So if we know the voltage on one side, we know the voltage on the other, right? Do we know the voltage on either of these sides, class? Which one? Yeah, we know the top one, the plus, has got 6 volts. Can you all see that? So what does the bottom one have? 4 volts.
I was thinking about the drop over that 6.
I thought you were just trying to get me anyway. It's 6 volts. Do you agree with that? If it's 6 volts, all right, you're ahead of me. It means what? Plus to minus 4 volts here. Do you all see that, class? That was close. All right. What's the current here? 4 over 6K. I'm just finishing up. You all with me, class? How many see that? Please just let me know. So I can. You all with me? I'm asking now for a reason. This is important. So if you know that current, how much current goes in or comes out of the negative? Zip, right? Where does it come from? Here. Right? Do we know the voltage across here? Yes, right? How do we get the output voltage? Start the negative, right? Negative volt, I'll go this way. Plus 6, right here, plus that current times 12K. Y'all with me? I'm over time now. How many see this? I'll see you on Friday. They're not tough, but you're gonna have to do the homework.